Hello, everyone. My name is Yifan Gong from Southeast University at China. I'm a PhD student in Professor Yamei Zhang's research team. It is a great honor for me to be the speaker to share the research of our team. Today, the topic of my presentation is a novel recycled concrete mixing approach offering engineering applicability. First is the research background. Construction industry plays a significant role in global urbanization, but it accounts for approximately 40% of global energy consumption and 36% of carbon emissions. In China, more than 15 billion tons of natural aggregates and 2.4 billion cubic meters of concrete has been produced per year. Therefore, energy conservation and carbon emission reduction in construction industry are necessary. On the other hand, the generation of construction and demolition waste has been increasing year by year. Utilizing the recycled coarse aggregates from the C and D waste could facilitate the reuse of C and D waste and conserve natural resources. However, the surface of recycled coarse aggregates are typically coated by a certain amount of old mortars, which has significantly inferior properties compared to the natural aggregates. So the properties of recycled coarse aggregates need to be enhanced. In recent decades, the scholars has proposed a series of treatment methods for the RCAS, such as mechanical grinding, acid soaking, and MICP treatment, and so on. But they still have some challenges, such as energy, labor, and time consumption, and high material cost, complex process, and so on. Limiting their widespread application in engineering projects. So the math of engineering suitability is imperative. In this case, we propose a combined adjustable cement slurry coating and mixing approach. Unlike with the normal mixing approach, which mix all the materials in the CSCM, the mixing water is divided into two stages based on the saturation degree of the RCAS. The proposed CSCM effectively prevents the excessive absorption of mixing water by RCAS, enabling the flexible adjustment of mixing water based on the variation in aggregate SD. Compared to the existing treatment methods for RCAS, the CSCM has the advantages such as high efficiency, cost effectiveness, ease of implementation. You know, just as we can see, there is no additional materials were used, and the process of the CSCM was finished within 6 minutes. But they still have a problem, just how to determine the stage 1 mixing water. Firstly, we conducted the aggregate coding test to evaluate the effect of different aggregate SD and stage 1 mixing water to cement ratio of slurry on the coating efficiency. Just as the result shows, as the water to cement ratio decreases, the coating efficiency initially increases and then decreases, indicating there is an optimal water to cement ratio. Moreover, an increase in aggregate SD initiates the efficiency. So why did we get such an experimental result? We focus our attention on the rheological properties of the cement slurry, just as the picture shows. The dynamic yield stress of the cement slurry exhibits two distinct stages when the water-cement ratio ranges from 0.48 to 0.35. The dynamic yield stress of cement slurry increases slowly. And when the water-cement ratio falls below to 0.35, the dynamic yield stress shows a repeat increase. This means the flowability of the cement slurry will significantly decrease. The interface defect level is highly correlated with the flowability of the cement slurry. When the aggregate SD is equal to 0%, and numerous pores and cracks were observed at the interface, and the samples with the water-cement ratio equal to 0.35, the defects are more pronounced. So reducing the water-cement ratio will aggravate the interface defects. However, highly aggregate SD, such as 100%, induces a water release effect. The dark zones near the boundary of the aggregates within cement slurry will become visible, and reducing the mechanical properties of the cement slurry. So we can know the coating efficiency is influenced by both the mechanical properties and the flowability of the cement slurry. As the water-cement ratio decreases, when the mechanical enhancement from coated cement slurry outweighs the negative effects of reduced flowability, the coating efficiency is enhanced. Otherwise, it decreases. Similar patterns apply to the aggregate SD. Based on the above result, the impact of CSCM significantly, the impact of CSCM on the properties of recycled aggregate concrete were involved. The result shows the CSCM significantly improves the compressive strength of the concrete compared to the normal mixing approach. The 28 days compressive strength of the concrete made by CSCM increased by 29%. And moreover, the compressive strength initially increased and then decreased as the water-cement ratio decreased. And as the aggregate SD increased from the 0% to 100%, the compressive strength of the concrete shows a significantly decrease. So the inference turned of the variable water to cement ratio to the aggregate SD on the compressive strength is consistent with the effect of the coating efficiency. And we conducted analyze from a micro perspective, and the result shows the CSCM significantly improves the micro mechanical properties of new ITZS, and indicating the bond between aggregates and new mortar were enhanced. Besides, due to the water release effect, the indentation models of the new ITZS significantly decreased. The distribution of the hydration products in the new ITZS approved the above result, and just as the picture shows, when the aggregate SD was equal to 0%, and in the concrete made by NMA, normal mixing branch, the hydration products in the new ITZS are primarily composed of CASH, AFT, and AFM. Only a small amount of CH and CSH was observed. However, when the concrete made by CSCM, the CSCM induces a annealing effect and facilitates the formation of CH and CSH at the new ITZS. When the aggregate SD reach to 100%, the annealing effect becomes invisible, and the porosity of the hydration products is in relative high. Above all, the CSCM induces a annealing effect and facilitates the formation of CH and CSH, which strengthens the bond between new mortar and the aggregate, thereby enhancing the composite strength of the concrete. However, the increase in aggregate SD diminishes the efficiency of the CSCM because of the water release effect. So we can conclude the two key factors of the CSCM implementing is selecting the optimal water cement ratio and maintaining the aggregate SD at a low level. But in the practical conditions, the aggregate SD can vary due to the environmental factors. So we establish a formula to calculate the optimal water cement ratio, just as the picture shows. When we obtain the recycled coarse aggregates, and usually we will test their basic properties, such as water absorption and so on. So we can determine the current aggregate SD. And then we can use this formula to calculate the optimal water cement ratio to corresponding the current state of the aggregate. And that's the way how to determine the stage 1 mixing order. Finally, its conclusions. And its conclusion we can draw. Firstly, the existing RCA treatment methods often require substantial labor and material resources, limiting their widespread application in engineering projects. And the second, the CSCM proposed in this study enhancing the properties of RYC by mixing water in 2 stages, with the amount adjustable based on variations in aggregate SD. And the third, the overall procedure of CSCM remains compact and offer advantages such as high efficiency, cost effectiveness, and ease of implementation, which are the critical concerns for practical applications in engineering. And finally, CSCM demonstrates the significant potential for the widespread application of RYC in practical engineering in the future. Yeah, that's all.
Hello, everyone. Yeah, I will not spend too much time presenting myself. I thank Marcelo for the introduction. But before that, I would really like to thank both the FIB and RYLEM for the invitation to be one of the speakers at this first peer-to-peer event. It's really an honor. You will see from my background that I have not had so much interaction with RYLEM. I'm more coming from the FIB side, but it's really an honor, and especially to be considered for the young members, which I think we will all realize soon. I have to admit that I'm probably no longer among the young members. So my presentation today will be on, let's say, more the application of recycled aggregate concrete structures in design. Yeah, so it's titled Design Code Provisions for Recycled Aggregate Concrete Structures. But also beyond that, beyond just giving an explanation of what are these design provisions here in particular, referring to the Eurocode 2 and the FIB Model Code 2020, I saw it as somehow also interesting or relevant, since I'm now, let's say, leaving this kind of, let's say, age gap of young engineers, to transfer my experience of how to exploit and take advantage of your research results for standardization, which, as we'll see, is one way of results exploitation. Exploitation does not need to be necessarily commercial. It can be for, let's say, policy making as it is defined, and standards are definitely a type of policy making. So this is also a kind of goal of my presentation. So I will start with just a very brief overview of CEN, the European Committee for Standardization, and how Eurocodes and Eurocode 2 fit into that landscape, how that functions, and then the FIB and how the Model Code 2020, let's say, also fits within the work of the FIB. Then I would just give a kind of brief presentation of the path that I personally took to get to the point of being able to contribute to these standards. And then I will, let's say, delve into particularly the provisions that are adopted both mostly now in the Eurocode 2, but also in the Model Code 2020, which are very similar or practically the same. And then we will finish with some, let's say, conclusions and takeaways. So first of all, CEN, the European Committee for Standardization, and now apologies for being kind of Europe-centric in this part, but this is the area that I worked in, is a committee for all European, or let's say harmonized European standards, and is constituted by all EU member states and the other countries that you see here listed on the screen. And within all the standards that CEN is responsible for adopting, there are the structural Eurocodes. Yeah? So probably a lot of you will know them. They go from Eurocode 0 to Eurocode 9, and they cover from basis of design, loads, concrete structures, steel structures, and so on. And if I just have pointer here, what is EN 1992? That is the Eurocode 2, and that is the Eurocode for concrete structures. And so each of these Eurocodes is actually developed and adopted by one of several subcommittees. So everything is under the umbrella of TC, that's Technical Committee 250, for all the structural Eurocodes. But then each of the Eurocodes, as you see, has their SC, that's subcommittee, right? And then here you will see that there is the subcommittee 2, which is the subcommittee of TC 250 responsible for Eurocode 2, that is for concrete structures. Currently chaired by Alejandro Perez from Polytechnic University of Madrid, but this is also, let's say, changing through over time. And you will see there are some other horizontal activity groups for bridges, fire, and so on. And so each of these groups then has a kind of work item on developing, updating each of these Eurocodes. And for Eurocode 2, or let's say structural Eurocodes 2, and then Eurocode 2 in particular, the one that we currently have in Europe is from 2004. But way back in 2010, how it starts is that one of the Director Generals of the European Commission issues a mandate to CEN, to the European Committee of Standardization, let's say, tasking them with developing a new standard. And in this case, they started all the way back in 2010 with a mandate that the overall objective is to initiate the process of further evolution of the Eurocodes. And as we see here, that was motivated by incorporating recent studies, research, and experience relevant to innovation in design and construction, meaning that already back then it was recognized that there were a lot of new materials, construction procedures, and structure types that were worthy of being incorporated into the Eurocodes, and recycled aggregate concrete being one of them. This was later updated with the mandate 515, but you will see that the process began now 16 years ago. And the new Eurocode 2 was voted and adopted in 2023. So you see that it's a 13-year process of just developing and adopting it, and it will not enter into force before Q3 of 2027. So you see that this is a very kind of marathon and long-term approach. But yeah, just to keep in mind what is happening. In terms of the FIB, the kind of crown jewel, the main document that the FIB produces is the model code. So this is a code on which, so since it's not a national code, it's a code on which national codes can be modeled, hence model code. And historically, the Eurocode has actually been based on the previous version of the model code. It all started in 78, then there was the model code 90, then, and this was SEB-FIB, and then it became the FIB, so there was model code 2010, and then Model Code 2020, which was actually also voted in 2023. After Model Code 2020, now there will only be partial updates. So there will not be a Model Code 2030 or 40, but now as partially one area is improved, shear, punching, fiber reinforced concrete, whatever, this part will be updated. So this will be going forward the way of updating the model code. And since in parallel the Euro codes were adopting all these new materials and so on, so the same happened in the model code. How I fit in all of that, just a kind of brief background. So I did my PhD and worked at the University of Belgrade and did research on time-dependent behavior under sustained load of full-scale recycled aggregate concrete members. Yeah, and let's say in the tradition of Roman engineers that had to be under the bridge when they were testing it. So too here you can see that I trusted in the material from the beginning, that it was something that had a future. Yeah. Kind of by chance, through a contact with Leonardo Todisco, who is a professor at Madrid, I was invited in 2017 to the first kickoff meeting of the FIB Young Members Group that was inaugurated then and started. And I was in the first period in the board of the FIB Young Members Group and the representative then of Serbia. That's where I was living and working. That is where I met Albert de la Fuente, the leader of our group here at UPC, and how I actually ended up being in Barcelona. Through the FIB, then I started joining some task groups. One of them was 2.1 serviceability models, because I was doing research on adapting, basically studying on databases, meta-analysis of shrinkage, creep, deflections of recycled aggregate concrete. Research was, let's say, targeted to calibrating existing models for that new material. And in one of the meetings of task group 2.1 in Lausanne, I presented some of this work, and in the audience was Jean-Michel Torrenti from Université Gustave Eiffel, at the time working on Eurocode 2 and on this Annex N, the future Annex N, for recycled aggregate concrete structures. So he suggested to me, why don't you join your national standardization body and through there join the working group for Eurocode 2, because we could use some help in developing this annex for recycled aggregate concrete. And from there, things went that together we developed this Annex N, wrote some background to it. There are some papers in structural concrete also explaining the rationale and the work behind all of that. And that launched, since Jean-Michel took over as commissioner of Commission 4, Concrete and Concrete Technology, the launching of Task Group 4.7, the structural application of recycled aggregate concrete, where I will say a few words later. We are now this year publishing a state-of-the-art bulletin on recycled aggregate concrete structures. So that's kind of the path that I took to be able to contribute to Annex N. And now I will show you, let's say, what it consists of, right? So the Eurocode 2, and then by extension also the model code, tried to incorporate a lot of different materials. You see here a lot of new annexes in the Eurocode and sections in the model code, such as steel fiber reinforced concrete, embedded FRP reinforcement. There is an annex on existing structures, stainless steel reinforcement, lightweight aggregate concrete structures, and recycled aggregate concrete structures. These annexes have different complexities. They either take the form of a kind of full mirroring of the text of the Eurocode, that they contain provisions on the basis of design, material properties, verification of ultimate and serviceability limit states, such as Annex L, Annex R. But some are more simple. So Annex M, which was in the current Eurocode directly in the text, now is a separate annex, actually just provides some equations that adapt existing models to lightweight aggregate concrete structures. So this was kind of the blueprint that we took for Annex N, recycled aggregate concrete structures. And you will see later how it is structured. It's actually very simple, that there are some limits of applicability, and then there are some modifications to apply to certain equations of the Eurocode for calculating recycled aggregate concrete structures. In terms of the background, I won't spend too much time because a lot of you already know, and some things were already presented by Yifan. But of course, recycled aggregates having this residual mortar that we aim basically to decrease presents some challenges, right? Mixed design, we said, and then effects on concrete properties that, if we were to generalize in a most general way, we would say the more recycled aggregate we use, the more reductions in properties we will see. Loss in compressive strength, modulus, shrinkage, creep, and so on, especially if we move from coarse to also fine recycled aggregate, that is recycled sand. And you can see here basically some tendencies of how much we'll be losing compressive strength. The fortunate thing is that when we go to the structural level, this effect is much diminished, because in a lot of ultimate limit states, actually we have the reinforcement which is governing the behavior. right? So in that case, if we achieve basically similar compressive strengths, there will not be almost any difference in structural behavior between natural and recycled aggregate concrete structures. Where there will be is basically in serviceability behavior, because recycled aggregate concrete will have, because of the less stiff aggregate, because of the residual mortar on the aggregate particles, it will have much higher shrinkage, creep, and a lower modulus of elasticity. So if we need to consider deflections, deformations, this is an area where, yes, there are important differences to be considered, right? So a lot of literature done over the years on all of the levels, from the material level, durability properties, time-dependent properties, structural behavior, and even case studies of applications in real structures. Within the Eurocode itself, there is a wider framework of standards that we have to fit within and comply with, such as EN 12620, that are the aggregates for concrete, that currently covers coarse recycled aggregate, provides this categorization of what are concrete particles, masonry particles, asphalt, and so on. So a kind of composition-based classification. And EN 206, which is the standard for concrete, which does have informative annex, meaning every country chooses whether to apply it and how, that does provide some limits to the use of recycled aggregate. But these limits are low, as you see here, and they depend on the exposure class. They are low because EN 206 does not contemplate the effect of recycled aggregate on properties. So the limit is there to ensure basically that within those limits, we don't see a loss in properties, and so you are kind of safe to use them. But now, through all the research that was done in the world, we can make models to take into account this change of properties and thereby allow higher replacement percentage. The important thing here is that this, for us, classifies the types of recycled aggregate, type A and type B, or type 1 and type 2. Type A being recycled concrete aggregate, so almost pure concrete waste, and type B being what we call mixed recycled aggregate, containing also masonry up to 30%. So let's say less stiff, more water absorption, and so on. And so this is basically Annex N. We're not going to read all of it, but it's very brief. It's very, let's say, concise. There is one textual part with 3 main clauses that here define, and we'll go into the substitution limits, so how much we can substitute to respect the Annex N, and then a table where we see some equations that basically modify the properties of recycled aggregate concrete, right? You see here that it's informative, and that within the context of Eurocode means that every country later will decide whether to adopt it or not, or if they adopt it, they can even change the contents, everything that's, so it's kind of orientative and a guidance on what to do. So in terms of limits of applicability, here we wanted to kind of stimulate the use of recycled aggregates, and everything is on a very kind of rudimentary level, depending on a parameter called alpha RA, and that's the substitution ratio of recycled aggregates. And it says here that the quantity of fine and coarse recycled aggregate divided by the total quantity of aggregates. So first of all, we are allowing for fine aggregates, but secondly, we have one parameter that kind of hides whether we are substituting fine and coarse or only coarse. Yeah? But this was also done on a purpose, as said, to kind of go one step ahead of EN 206, which will be updated and is now in the process of updating, but also to, let's say, stimulate recycling. So there are some limits that say if you use up to 20% of recycled aggregate, but total that can be 20 and 20, fine and coarse, or if it's only coarse, depending on the ratio between fine and coarse, you can end up using 35–40% of coarse aggregate and still be within the limit. There are no change in the mechanical properties. This is what all the literature shows. If you go up to 40, then you use what is in the table. I mean, you change the properties based on the equations. If you go above 40, you have to test. Yeah? And this is for reinforced concrete. For pre-stressed concrete, everything is slashed by 50%, simply because there were not sufficient results to back it up, although the effects on the concrete itself should not change. And this is for type A aggregate, the recycled concrete aggregate. If you want to go to mixed, you again reduce everything by 50%. A lot of it was based, and the Annex N as well, on research done within a French national project called RYC Beton. Yeah? So they actually provided different separate substitution ratios for coarse and fine aggregates that we try to average out and propose these limits. So the particular properties, just to go through a few, for example, compressive strength, that's an input in the code. So there is really no need to change anything. The only thing is that we limited the applicability to class C50, so 50 MPa concrete, because of the scarcity of results on high strength and difficulty of making high strength recycled aggregate concrete. It can be used, but you have to do testing. Since the variability, let's say the statistical distributions are similar or same between natural aggregate concrete and recycled aggregate concrete, there are no changes in coefficient of variation, so partial factor, material partial factors can change the same. For modulus of elasticity, as we said, they are significant. There are reductions in the modulus of elasticity because of the aggregates. And here we carried out a meta-analysis of collecting results from literature, splitting them into groups of percentage ratios, and calibrating simply empirically a reduction coefficient. So Ka times FCM to the power of 1/3 is the typical expression, where Ke depends on the natural aggregates, but you have a reduction of 1 minus 0.25 alpha. Remember that alpha goes up to 0.4, that you can use it. So actually it's a 10% reduction. It's not so dramatic when you are within the limits of Eurocode. Stress-strain relationships, literature shows an increase in both the peak and ultimate strain. So there are some increases of 1 plus 0.33 alpha RA for the peak and ultimate strain. There are increases in shrinkage and creep. Here we had also carried out already meta-analysis both within the Vesibeton project and our own research in Belgrade and Barcelona. So we kind of compared at the right image the two expressions that the two research showed, and they coincided quite a bit. And so we proposed an increase where you calculate shrinkage as if it were natural aggregate concrete, and then you multiply it with 1 plus 0.8 alpha. That is a significant increase, because if you limit to 0.4, then you are 32% increasing shrinkage. Very similar for creep. The only thing is that it's slightly lower, so it's 1 plus 0.6. So it's a kind of 25% increase of the creep coefficient, which you calculate as if it were natural aggregate concrete. Again, everything is in the backgrounds, but comparing different meta-analyses that analyzed a lot of experimental results. Flexural and shear strength. So flexural strength depends on compressive strength. There is basically no change there. In shear, there were also studies on databases that show that the partial factor for shear should be increased, but linearly, going from 0 to 100 recycled aggregates, from 1.5 to 1.6 and 1.7. So we opted for, instead of changing a partial factor, which is a kind of bigger thing in Eurocode, to making this kind of linear decrease in 1 minus 0.2 alpha, and then the typical expression that is for natural aggregate concrete. Again, if we go to 0.4 of recycled aggregates, which is the limit, this is an 8% reduction in members not requiring shear reinforcement, but it's there. In deflections, there are changes, of course, because even if you introduce higher shrinkage, higher creep, lower modulus, you still have, let's say, an underestimation of deflection. So there is a loss of decrease in tension stiffening. And so this beta coefficient within zeta, which is the interpolation coefficient for curvatures or deflections, for long-term, for sustained loading, was reduced from 0.5 to 0.25. Again, this is all empirical fitting on meta-analysis of databases of collected results. And then the same was done on the simplified deflection control by span depth ratio, which was developed by Alejandro Perez, the now chairman of SC2. And it was just readjusted for recycled aggregates by whatever you get for natural aggregate concrete. It turns out you have to divide the standards by 1 plus 0.12 alpha. So again, the expressions are very similar, simple and direct to use. Something very similar is in the model code, only there we were not bound by EN 206 and other standards. So actually, everything is still defined in a coefficient of total substitution ratio, tau TRA, total recycled aggregate concrete, but actually the limitations are in terms of this coarse recycled aggregate. And here we allow up to 100% of coarse aggregate substitution, but if you would go into the text, you will see that the expressions are exactly the same. The background is in this article, in the Eurocode 2 background. We are this year publishing a bulletin from Task Group 4.7. And I also have to mention RYLEM Technical Committee 273 that this year and last year actually published their 2-volume reports on structural behavior and innovation of recycled aggregate concrete. We had a lot of kind of shared members between TG 4.7 and this RYLEM TC. So that was also a good collaboration. And I think the reports complement each other. And so just as to conclude, I would say that it's crucial to develop standards for new materials. We see that this takes a long time and it is a key barrier to market uptake. A basis is sound science and useful and usable results, so thinking kind of oriented towards applicability. It's important, I think, to carry out this meta-analysis once a lot of research is done and to model, let's say, to develop models, correct existing ones or calibrate them if we have a hypothesis of some simple change. Yeah. And just reiterate that it's a great way for involving young members that developing of standards is exploitation of research results. And I would invite people also to reach out. Task Group 4.7 is reorienting now its work towards aggregates in general because we completed the state-of-the-art report on RYC. But there is a lot of space, and this is, I think, in particular a group that was coordinated by then a young member and is very open. And I think the majority are young members. Our meetings are online, so not so demanding on traveling. And yeah, once again, thank you all for your attention and open to all questions.